Hey students, this is lesson 422, exponential growth and decay. What we're going to learn today is that there's two kinds of exponential growth, increasing exponential growth and decreasing exponential growth. And we're going to look at a couple examples of each of these. This first example here, this comic book collection, each time we're adding 4, which means this is growing at a constant rate. When that happens, that's a linear situation. And the equation for this situation would be, notice that the number of comic books is just 4 times however many weeks we have. So it would just be comics is equal to 4 times however many weeks. Okay, in this next situation, the fruit fly population that we looked at in the previous exercises, we know that to get from 2 to 4 and then 4 to 8, we're actually multiplying by 2 each time. When you're multiplying by 2 and it's going up, that means that it's growing at that rate. We call that either exponential increase or exponential growth. And in this problem, we get that exponential, the expression for that exponential growth is we need to multiply by 2 as many weeks as we have the flies. So the expression is an exponential expression. And it would be something like this: 2 to the W weeks equals flies. All right. What we're going to do, what I'm going to do is show you 2 examples now, one of exponential growth and then one of decay. I'm going to skip ahead a little bit to page 13, and we're going to look at this problem right here that has to do with the number of weeks in the plants that we have. It says a botanist recorded the number of duckweed plants in a pond at the same time each week. It says look at the second row of the table. By what number do you multiply each value to get to the next value? So we want to know what number we multiply by 32 to get to 48. So to figure that out, we're going to do 48 divided by 32. And if you use your calculator, you will find that that equals 1.5. So we are multiplying by 1.5 each time. And then the next part says predict the number of plants in the 5th week. So if we want, all we have to do is take 162 times 1.5. And I can do that over here. And that equals 240. 243. Okay? That doesn't seem right. It should be an even number. All right, so I just checked my math there. It's right, 243 in the 5th week. And then it says, which expression describes the number of plants in the pond after W weeks? So we are increasing by multiplying by 1.5 every week. So that suggests that it's an exponent because we keep multiplying by the same base. And our base is the number we're multiplying by, 1.5. So if I look at these expressions, which has a base of 1.5? And that would be this one here. And we also know it's this expression because this expression has an exponent, and to continually multiply by 1.5, we need an exponent. All right, that's an example of exponential growth. We're now going to look at an example of exponential decay, and I'm going to go back to this one right here. Imagine that a super ball is dropped onto concrete from a height of 1 meter and is allowed to bounce repeatedly. Suppose the height of each bounce is 0.8 times the height of the previous bounce. 0.8 is the same as 80%, so you could think of this as 80% also. 80% of the height of the previous. To understand how the height changes, you can imagine sending a piece of putty through a times 0.8 machine repeatedly. So how high does the ball rise on the first bounce? So it starts at 1 meter, and I think I'm going to change that to centimeters. 1 meter is the same as 100 centimeters. I think that'll So if we start at 100 centimeters and we multiply by 0.8, that equals 80 centimeters. So after one bounce, it's at 80. On the second bounce, we're going to do 80 times 0.8, and that's equal to 64 centimeters. On the third bounce, we're going to do 64 times 0.8, and I want to show you how to do this on your calculator now. So remember, we started at 100, so I'm just going to put 100 in there, hit enter. And to get 80% of that, we're multiplying by 0.8 every time. And so there's the 80, the first bounce. And we multiply by 0.8 again, and that's 64, the second bounce. And then the third bounce is 51.2, and so on. So on the third bounce, it's 51.2. And then it says complete the table to show how the ball's height in centimeter changes with each bounce. So here we're going to multiply by 0.8 3 times on the third bounce. And that is the same as 100 times 0.8 the third. On the fourth bounce, we're going to multiply by 0.8 4 times. And I'm not going to do all that, but we can see the expression is just changing by adding 1 to the power for each bounce. So on the 10th bounce, if we follow this reasoning, notice that the power is the same as the number of bounces, so we need to do 100 times 0.8 for the 10th power to get that. All right, so how high does the ball rise on the 10th bounce? 100 times 0.8. The 10th equals so it's about 10.7, we'll round that to. It says how many times do you think the ball will bounce before coming to a rest? It's kind of hard to tell here because according to our situation, and I can show you that on the calculator, it would seem like, so now if I multiply this by 0.8 again, so that's the 11, and if I keep hitting enter, it keeps getting smaller, but, and I really should count how many there are. When it comes to rest is when you get to 0, and theoretically you really will never get to 0, but you have to think just, well, when is it such a small amount that the ball's just going to stop bouncing? And your guess is as good as mine, but I'm thinking like maybe around 20 bounces. So if you do 100 times 0.8 20th, it's a pretty small number. It's about 1 centimeter, so it probably isn't going to bounce much more than that. So 20 or so bounces. And it says use the pattern in the right column of your table to write an expression for the ball's height on the nth bounce. Notice we always took 100 and then we multiplied by 0.8. And the only difference between all of the expressions in the table is we kept changing this. So, and that changed according to what bounce we're on. So that can be our variable n. And that goes there. Assuming the ball continues to bounce, use your expression to find the height of the ball on the 35th bounce. So we want to do 100 times 0.8 35th. And let's see what that is. I'm going to go second enter, and that's going to repeat, and then I'm just going to delete that and put a 35 there. And it looks like it's almost 0.04. Does that answer surprise you? And Yeah, it seems like it's getting pretty low. But I don't think a ball would actually bounce 35 times, so I don't know. Now, one thing you might have noticed in this is that the numbers kept going down. And if you look at this table, or if you think about how high it was after each bounce, the numbers kept decreasing. We can look at this table again. So we took 100, entered, and then we multiplied by 0.8. And every time we hit enter, the numbers get smaller. When that happens, that's called exponential decrease or exponential decay. And that happens when you multiply by a number like 0.8 that's between 0 and 1. As the height gets smaller with each bounce, and that's a situation of exponential decay. All right, I think that's going to be it today. You can read the rest of this and get back at it next time we meet in class.